extremely pedantic colleague who will point out, okay, did you really mean this? Like, what happens if this is zero? Okay, did you? How do you justify this? Um, so Lean has a lot of automation in it to try to be less annoying. Um, so, for example, every mathematical object has to come with a type. Like if I talk about x, is x a real number or a natural number or a function or something? Um, if you write things informally, it's often in terms of context. You say, clearly x is equal to let x be the sum of y and y and z were already real numbers, so x should also be a real number. So Lean can do a lot of that, but every so often it says, wait a minute, can you tell me more about what this object is, what type of object it is? You have to think more at a philosophical level, well, not just sort of the computations that you're doing, but sort of what each object actually is in some sense.
Is he using something like LLMs to do the type inference, or like you mentioned with a real number?
It's using much more traditional, what's called good old-fashioned AI. Yeah, you can represent all these things as trees, and there's always algorithm to match one tree to another tree.
So it's actually doable to figure out if something is a real number
Yeah,
or a
because
natural
yeah,
number.
every object sort of comes with a history of where it came from, and you can kind of trace it.
Oh, I see. Got it.
Yeah, so
Got it. Got it. Got it.
it's designed for reliability. So modern AIs are not used in it's a disjoint technology. People are beginning to use AIs on top of Lean. So when a mathematician tries to program a proof in Lean, often there's a step. Okay, now I want to use the fundamental theorem of calculus, say, okay, to do the next step. So the Lean developers have built this massive project called Mathlib, a collection of tens of thousands of useful facts about mathematical objects. And somewhere in there is the fundamental theorem of calculus, but you need to find it. So a lot of the bottleneck now is actually lemma search. There's a tool that is in there somewhere, and you need to find it. And so there are various search engines specialized for Mathlib that you can do. But there's now these large language models that you can say, okay, I need the fundamental theorem of calculus at this point. And it was like, okay, for example, when I code, I have GitHub Copilot installed as a plugin to my IDE. And it scans my text and it sees what I need. It says, I might even type, okay, now I need to use the fundamental theorem of calculus. Okay. And then it might suggest, okay, try this. And like maybe 25% of the time, it works exactly. And then another 10, 50% of the time, it doesn't quite work, but it's close enough that I can say, oh, yeah, if I just change it here and here, it'll work. And then like half the time, it gives me complete rubbish. But people are beginning to use AIs a little bit on top. Um, mostly on the level of basically fancy autocomplete. That you can type half of one line of a proof and it will tell you.
Yeah, but a fancy, especially fancy with the sort of capital letter F, is remove some of the friction
Yeah.
mathematician might feel when they move from pen and paper to formalizing.
Yes. Yeah. So right now I estimate that the time and effort taken to formalize a proof is about 10 times the amount taken to write it out. But yeah. So it's doable, but you don't, it's annoying.
But doesn't it like kill the whole vibe of being a mathematician?
Yeah.
Just
So, I mean,
having a pedantic coworker.
right. Yeah. If that was the only aspect of it. Okay. But, okay, there's some cases where it's actually more pleasant to do things formally. So there was a theorem I formalized, and there was a certain constant 12 that came out in the final statement, and so this 12 had to be carried all through the proof, and like everything had to be checked that it goes all these other numbers that had to be consistent with this final number 12. And then so we wrote a paper through this theorem with this number 12, and then a few weeks later, someone said, "Oh, we can actually improve this 12 to an 11 by reworking some of these steps." And when this happens with pen and paper, like every time you change a parameter, you have to check line by line that every single line of your proof still works. And there can be subtle things that you didn't quite realize, some properties of number 12 that you didn't even realize that you were taking advantage of. And so a proof can break down at a subtle place. So we had formalized the proof with this constant 12. And then when this new paper came out, we said, oh, okay, let's. So that took like 3 weeks to formalize, and like 20 people to formalize this original proof. I said, oh, but now uh, let's update the 12 to 11. And what you can do with Lean is that you just in your headline theorem you change the 12 to an 11, you run the compiler, and like of the thousands of lines of code you have, 90% of them still work, and there's a couple that are lined in red. Now I can't justify these steps, but it immediately isolates which steps you need to change. But you can skip over everything which works just fine. And if you program things correctly with sort of good programming practices, most of your lines will not be red. And there'll just be a few places where I mean, if you don't hard code your constants, but you sort of
Hmm.
um, you use smart tactics and so forth. Yeah, you can localize the things you need to change to a very small period of time. So it's like within a day or two, we had updated our proof. Because this is a very quick process. You make a change. There are 10 things now that don't work. For each one, you make a change, and now there's 5 more things that don't work. But the process converges much more smoothly than with pen and paper.
So that's for writing. Are you able to read it? Like if somebody else sends a proof, are you able to like what's the versus paper and
Yeah, so the proofs are longer, but each individual piece is easier to read. So if you take a math paper and you jump to page 27 and you look at paragraph 6 and you have a line of text of math, I often can't read it immediately because it assumes various definitions, which I have to go back and maybe on 10 pages earlier this was defined. And the proof is scattered all over the place. And you basically are forced to read fairly sequentially. Um, it's not like, say, a novel where, like, in theory, you could open up a novel halfway through and start reading. There's a lot of context. But when a in Lean, if you put your cursor on a line of code, every single object there, you can hover over it and it would say what it is, where it came from, where stuff is justified. You can trace things back much easier than sort of flipping through a math paper. So one thing that Lean really enables is actually collaborating on proofs at a really atomic scale that you really couldn't do in the
Mhm.
past. So traditionally, with pen and paper, when you want to collaborate with another mathematician, either you do it at a blackboard where you can really interact, but if you're doing it sort of by email or something, um, basically, you have to segment it. So I'm gonna finish section 3, you do section 4, but you can't really sort of work on the same thing collaboratively at the same time. But with Lean, you can be trying to formalize some portion of the proof and say, I got stuck at line 67 here. I need to prove this thing, but it doesn't quite work. Here's the 3 lines of code I'm having trouble with. But because all the context is there, someone else can say, oh, okay, I recognize what you need to do. You need to apply this trick or this tool. And you can do extremely atomic level conversations. So because of Lean, I can collaborate with dozens of people across the world, most of whom I don't have never met in person, and I may not know actually even whether they're how reliable they are in their in the proof they give me. But Lean gives me a certificate of trust. So I can do trustless mathematics.
so there's so many interesting questions. So one, you're known for being a great collaborator. So what is the right way to approach solving a difficult problem in mathematics when you're collaborating? Are you doing a divide and conquer type of thing, or are you focused in on a particular part and you're brainstorming?
There's always a brainstorming process first. Yeah. So math research projects, sort of by their nature, when you start, you don't really know how to do the problem. Um, it's not like an engineering project where somehow the theory has been established for decades and its implementation is the main difficulty. You have to figure out even what is the right path. So this is what I said about cheating first. It's like to go back to the bridge building analogy. So first assume you have infinite budget and like unlimited amounts of workforce and so forth. Now can you build this bridge? Okay. Now have infinite budget but only finite workforce. Right now can you do that and so forth? Um, I mean, of course, no engineer can actually do this because they have fixed requirements. Yes, there's this sort of jam sessions always at the beginning where you try all kinds of crazy things and you make all these assumptions that are unrealistic, but you plan to fix later. And you try to see if there's even some skeleton of an approach that might work. And then hopefully that breaks up the problem into smaller sub problems, which you don't know how to do, but then you focus on the sub ones. And sometimes different collaborators are better at working on certain things. Um, so one of my theorems I'm known for is a theorem of Ben Green, which is now called the Green-Tau theorem. Um, it's a statement that the primes contain arithmetic progressions of any length. So it was a modification of this theorem of Semereti. And the way we collaborated was that Ben had already proven a similar result for progressions of length 3. He showed that sets like the primes contain lots and lots of progressions of length 3, even subsets of the primes, certain subsets do. Um, but his techniques only worked for length 3 progressions. They didn't work for longer progressions. But I had these techniques coming from ergodic theory, which is something that I had been playing with and I knew better than Ben at the time. Um, and so if I could justify certain randomness properties of some set relating to the primes, like there's a certain technical condition which if I could have it, if Ben could supply me this fact, I could conclude the theorem. But what I asked was a really difficult question in number theory, which um, he said, no, there's no way we can prove this. So he said, can you prove your part of the theorem using a weaker hypothesis that I have a chance to prove it? And he proposed something which he could prove, but it was too weak for me. I said, I can't
Yeah.
use this. So there was this conversation going back and forth. Um, it's sort of a
Different
haggling.
cheats too.
Yeah, yeah, yeah. I want to
Different.
cheat more. He wants to cheat less. Okay,
Yeah.
but eventually we found a property which A he could prove and B I could use, and then we could prove our theorem. And yeah, so there's there are all kinds of dynamics. I mean, it's every collaboration has some story. No two are the same.
And then on the flip side of that, like you mentioned with lean programming,
Mm.
now that's almost like a different story because you can create, I think you've mentioned a kind of a blueprint
Mhm. Right.
for a problem, and then you can really do a divide and conquer
Yeah.
with lean where you're working on separate parts
Right.
and they're using the computer system proof checker essentially
Yeah.
to make sure that everything is correct along the
Yeah.
way.
So it makes everything compatible and yeah, and trustable. Yeah. So currently, only a few mathematical projects can be cut up in this way. At the current state of the art, most of the lean activity is on formalizing proofs that have already been proven by humans.
Mhm.
A math paper basically is a blueprint in a sense. It is taking a difficult statement like a big theorem and breaking up into maybe 100 little lemmas. Um, but often not all written with enough detail that each one can be sort of directly formalized. A blueprint is like a really pedantically written version of a paper where every step is explained to as much detail as possible, and trying to make each step kind of self-contained, um, and or depending on only a very specific number of previous statements that have been proven, so that each node of this blueprint graph that gets generated can be tackled independently of the others. And you don't even need to know how the whole thing works. So it's like a modern supply chain. Like if
Mhm.
you want to create an iPhone or some other complicated object, no one person can build a single object, but you can have specialists who just, if they're given some widgets from some other company, they can combine them together to form a slightly bigger widget.
I think that's a really exciting possibility because you can have, if you can find problems that could be
Right.
broken down this way, then you can have, thousands of contributors, right? It
Yes,
could be
yes,
completely
yes. Yeah.
distributed.
So I told you before about the split between theoretical and experimental mathematics. And right now, most mathematics is theoretical and only a tiny bit is experimental. I think the platform that Lean and other software tools, GitHub and things like that, they will allow experimental mathematics to scale up to a much greater degree than we can do now. So right now, if you want to um, do any mathematical exploration of some mathematical pattern or something, you need some code to write out the pattern. And I mean, sometimes there are some computer algebra packages that help, but often it's just one mathematician coding lots and lots of Python or whatever. And because coding is such an error-prone activity, it's not practical to allow other people to collaborate with you on writing modules for your code. Because if one of the modules has a bug in it, the whole thing is unreliable. Um, so so you get these bespoke spaghetti code that written by not professional programmers, but by mathematicians, and they're clunky and slow, and so because of that, it's hard to really mass produce experimental results. Um, but yeah, but I think with Lean, I mean, so I'm already starting some projects where we are not just experimenting with data, but experimenting with proofs. So I have this project called the Equational Theories Project. Basically, we generated about 22 million little problems in abstract algebra. Maybe I should back up and tell you what the project is. Okay, so abstract algebra studies operations like multiplication and addition and their abstract properties. Okay, so multiplication, for example, is commutative. X times y is always y times x. These for numbers. And it's also associative. X times y times z is the same as x times y times z. So these operations obey some laws and they don't obey others. For example, x times x is not always equal to x. So that law is not always true. So given any operation, it obeys some laws and not others. Um, and so we generated about 4,000 of these possible laws of algebra that certain operations can satisfy. And our question is, which laws imply which other ones? So for example, does commutativity imply associativity? And the answer is no, because it turns out you can describe an operation which obeys the commutative law but doesn't obey the associative law. So by producing an example, you can show that commutativity does not imply associativity. But some other laws do imply other laws by substitution and so forth. And you can write down some algebraic proof. So we look at all the pairs between these 4,000 laws, and there's about 22 million of these pairs. And for each pair, we ask, does this law imply this law? law? If so, give a proof. If not, give a counterexample.
Mhm.
So 22 million problems, each one of which you could give to an undergraduate algebra student, and they had a decent chance of solving the problem. Although there are a few, of these 22 million, there are like a hundred or so that are really quite hard. Okay, but a lot are easy. And the project was just to work out to determine the entire graph, like which ones imply which other ones.
That's an incredible project, by the way. Such a good idea, such a good test of the very thing we've been talking about at a scale that's remarkable.
Yeah, so it would not have been feasible. I mean, the state of the art in the literature was 15 equations and sort of how they imply. That's sort of at the limit of what a human with pen and paper can do. So you need to scale it up. So you need to crowdsource, but you also need to trust all the. I mean, no one person can check 22 million of these
Mhm.
proofs. Okay? You need it to be computerized, and so it only became possible with Lean. We were hoping to use a lot of AI as well. So the project is almost complete. So of these 22 million, all but two have been settled. Um, and
Wow.
well, actually, and of those two, we have a pen and paper proof of the two, and we're formalizing it. In fact, this morning I was working on finishing it. So we're almost done on this.
That's incredible.
It's yeah, fantastic.
How many people were able to get?
About 50, uh, which in mathematics is considered a huge number.
It's a huge number. That's
Yeah,
crazy.
yeah. So we're gonna have a paper with 50 authors. And a big appendix of who contributed what.
Here's an interesting question, not to maybe speak even more generally about it. When you have this pool of people, is there a way to organize the contributions by level of expertise of the people, of the contributors? Now, okay, I'm asking you a lot of pothead questions here, but I'm imagining a bunch of humans and maybe in the future some AIs.
Yeah.
Can there be like an ELO rating type of situation where like a gamification of this?
The beauty of these lean projects is that automatically you get all this data. So like everything's to be uploaded to this GitHub, and GitHub tracks who contributed what. So you could generate statistics from at any later point in time. You can say, oh, this person contributed this many lines of code or whatever. I
Mhm.
mean, these are very crude metrics. I would definitely not want this to become like part of your tenure review or something. Um, but I mean, I think already in enterprise computing, right? People do use some of these metrics as part of the assessment of performance of an employee. Again, this is a direction which is a bit scary for academics to go down. We don't like metrics so much.
And yet, academics use metrics. They just use old ones. Number of papers.
Yeah, it's true. It's true that yeah. I mean,
It feels like this is a metric, while flawed, is going in the more in the right direction, right?
yeah,
It's an interesting. I mean, at least it's a very interesting metric.
yeah. I think it's interesting to study. I mean, I think you can do studies of whether these are better predictors. There's this problem called Goodhart's law. If a statistic is actually used to incentivize performance, it becomes gamed, and then it is no longer a useful measure.
Oh, humans always
Yeah, no, I mean,
always gaming the
it's rational.
incentives.
So what we've done for this project is self-report. So there are actually these standard categories from the sciences of what types of contributions people give. So there's this concept and validation and resources and coding and so forth. So we there's a standard list of 12 or so categories. And we just ask each contributor to there's a big matrix of all the authors in all the categories just to tick the boxes where they think that they contributed. And just to give a rough idea, like, oh, so you did some coding and you provided some compute, but you didn't do any of the pen and paper verification or whatever. And I think that works out. Traditionally, mathematicians just order alphabetically by surname. So we don't have this tradition as in the sciences of lead author and second author and so forth, like, which we're proud of. We make all the authors equal status, but it doesn't quite scale to this size. So a decade ago, I was involved in these things called polymath projects. It was the crowdsourcing mathematics, but without the lean component. So it was limited by you needed a human moderator to actually check that all the contributions coming in were actually valid. And this was a huge bottleneck, actually. Um, but still, we had projects that were, 10 authors or so. But we had decided at the time not to try to decide who did what, but to have a single pseudonym. So we created this fictional character called DHJ Polymath. In the spirit of Bourbaki, Bourbaki is the pseudonym for a famous group of mathematicians in the 20th century. And so the paper was authored under pseudonym, so none of us got the author credit. This actually turned out to be not so great for a couple of reasons. So one is that if you actually wanted to be considered for tenure or whatever, you could not use this paper in your as your submitted as one of your publications because you didn't have the formal author credit. Um, um, but the other thing that we've recognized much later is that when people referred to these projects, they naturally refer to the most famous person who was involved in the project. Oh, yeah, so this was Tim Gower's Plymouth project, or this
Mhm.
was Terence Tao's Plymouth project, and not mention the other 19 or whatever people that were involved.
Ah, yeah.
So we're trying something different this time around where we have everyone's an author, but we will have an appendix with this matrix, and we'll see how that
Well,
works.
I mean, so both projects are incredible. Just the fact that you're involved in such huge collaborations. But I think I saw a talk from Kevin Buzzard about the lean programming language just a few years ago, and he was saying that this might be the future of mathematics. And so it's also exciting that you're embracing one of the greatest mathematicians in the world, embracing this, what seems like the paving of the future of mathematics. So I have to ask you here about the integration of AI into this whole process. So DeepMind's Alpha Proof was trained using reinforcement learning
Mhm.
on both failed and successful formal lean proofs
Mhm.
of IMO problems. So
Yes,
this
yes,
is
yes.
sort of high level high school,
Oh, very high level. Yes.
very high level high school level mathematics problems. What do you think about the system, and maybe what is the gap between this system that is able to prove the high school level problems
Right.
versus graduate level problems?
Yeah, the difficulty increases exponentially with the number of steps involved in the proof. It's a combinatorial explosion. Right? So the thing with large language models is that they make mistakes, and so if a proof has got 20 steps, and your large language model has a 10% failure rate at each step of going in the wrong direction, like uh, it's just extremely unlikely to actually reach the end.
Actually, just to take a small tangent here, is how hard is the problem of mapping from natural language to the formal program?
Oh, yeah, it's extremely hard actually. Natural language, it's very fault tolerant. Like you can make a few minor grammatical errors, and a speaker in the second language can get some idea of what you're saying. Um, yeah, but formal language, yeah, if you get one little thing wrong, like the whole thing is nonsense.
Got it.
Even formal to formal is very hard. There are different incompatible proof assistant languages. There's Lean, but also Coq and Isabel and so forth. And actually, even converting from a formal language to formal language is an basically unsolved problem.
That is fascinating. Okay, so but once you have an informal language, they're using um, their RL trained model, so something akin to Alpha Zero that they use for
Yes,
Go, to then try to come up with proofs. They also have a model, I believe it's a separate model for geometric
yes.
problems. So, what impresses you about this system, and what do you think is the gap?
Yeah. We talked earlier about things that are amazing over time become kind of normalized. So yeah, now somehow it's of course geometry is a solvable problem.
Right, that's true. That's true. I mean, it's still beautiful
Yeah, yeah,
to
no,
look at the work they're doing.
these are great works. It shows what's possible. I mean, the approach doesn't scale currently. Yeah, 3 days of Google's server time to solve one high school math problem. Yeah, this is not a scalable prospect, especially with the exponential increase in as the complexity increases.
We should mention that they got a silver medal performance,
The equivalent of, I mean, yeah,
equivalent of a
I
silver
mean,
medal performance.
so first of all, they took way more time than was
Mm.
allotted, and they had this assistance where the humans started helped by formalizing. But uh, yeah, also they're giving themselves full marks for the solution, which I guess is formally verified. So I guess that's fair. Um, yeah. There are efforts. There will be a proposal at some point to actually have an AI math Olympiad where, at the same time as the human contestants get the actual Olympiad um, problems, AIs will also be given the same problems with the same time period, and the outputs will have to be graded by the same judges, um, and which means that it will have to be written in natural language rather than formal language.
Oh, I hope that happens. I hope
Yeah,
that this IMO happens. I hope next one.
it won't happen this IMO. The performance is not good enough in the time period, and um, but there are smaller competitions. Yeah, there are competitions where the answer is a number rather than a long form proof. Um, and AIs are actually a lot better at problems where there's a specific numerical answer because it's easy to do reinforcement learning on it. Yeah, you got the right answer, you got the wrong answer. It's a very clear signal. But a long form proof either has to be formal, and then the lean can give it thumbs up, thumbs down, or it's informal. But then you need a human to grade it
Hmm.
to tell. And if you're trying to do billions of reinforcement learning, runs, you can't hire enough humans to grade those. I mean, it's already hard enough for the large language models to do reinforcement learning on just the regular text that people get. But now if you actually hire people, not just give thumbs up, thumbs down, but actually check the the output mathematically, yeah, that's too expensive.
So if we just explore this possible future, what is the thing that humans do that's most special in mathematics? So that you could see AI not cracking for a while. So inventing new theories, so coming up with new conjectures versus proving the conjectures,
Right.
building new abstractions, new representations, maybe an AI turnstile with seeing new connections between disparate fields.
It's a good question. I think the nature of what mathematicians do over time has changed a lot. Um, so 1,000 years ago, mathematicians had to compute the date of Easter, and there's really complicated calculations. But it's all automated, been automated for centuries. We don't need that anymore. They used to navigate to do spherical navigation, spherical trigonometry to navigate how to get from the old world to the new, or something. Very complicated calculations again been automated. Um, even a lot of undergraduate mathematics, even before AI, like Wolfram Alpha, for example, is not a language model, but it can solve a lot of undergraduate level math tasks. So on the computational side, verifying routine things like having a problem and say, here's a problem in partial differential equations. Could you solve it using any of the 20 standard techniques? And
Hmm.
they say, yes, I've tried all 20, and here are the 100 different permutations, and here's my results. And that type of thing, I think it will work very well. Type of scaling to once you solve one problem to make the AI attack 100 adjacent problems. The things that humans do still so where the AI really struggles right now um, is knowing when it's made a wrong turn. Um, and it can say, "Oh, I'm going to solve this problem. I'm going to split up this problem into these two cases. I'm going to try this technique." And sometimes, if you're lucky, and it's a simple problem, it's the right technique, and you solve the problem. And sometimes it will have a problem. It would propose an approach which is just complete nonsense. But like it looks like a proof. So this is one annoying thing about LLM generated mathematics. So um,
Yeah.
we've had human generated mathematics that's very low quality. Like submissions of people who don't have the formal training and so forth. But if a human proof is bad, you can tell it's bad pretty quickly.
Hmm.
It makes really basic mistakes. But the AI generated proofs, they can look superficially flawless. And it's partly because that's what the reinforcement learning has actually trained them to do, to make things to produce text that looks like what is correct, which for many applications is good enough. Um, so the errors are often really subtle, and then when you spot them, they're really stupid. Like no human would have actually made that mistake.
Yeah, it's actually really frustrating in the programming context because I program a lot, and
Mhm.
yeah, when a human makes when low quality code, there's something called code smell, right? You could
Yes,
tell, you
yeah,
could tell
yeah,
immediately, like,
right, yeah,
okay, there's
yeah.
signs. But with AI generate code,
They're odorless.
and then you're right.
Yeah,
Eventually, you find an obvious dumb thing that just looks
yeah,
like good code.
yeah. So
It's very tricky to and frustrating for some reason to
yeah,
have
so
to work
yeah, so the sense of smell. Okay, there you go.
Yes. Yes.
This is one thing that humans have, and there's a metaphorical mathematical smell that
Yeah.
uh, there's we it's not clear how to get the AI to duplicate that. Eventually, I mean, so the way AlphaZero and so forth to make progress on Go and chess and so forth is in some sense they have developed a sense of smell for Go and chess positions.
Mhm.
That this position is good for white, this is good for black. They can't enunciate why, um, but just having that sense of smell lets them strategize. So if AIs gain that ability to sort of a sense of viability of certain proof strategies, so you can say, I'm going to try to break up this problem into two small subtasks, and they can say, oh, this looks good. The two tasks look like they're simpler tasks than your main task, and they still got a good chance of being true. So this is good to try. Or no, you made the problem worse because each of the two subproblems is actually harder than your original problem, which is actually what normally happens if you try a random thing to try. Normally, it's very easy to transform a problem into an even harder problem.
Mhm.
Very rarely do you transform to a simpler problem. Um, yeah, so if they can pick up a sense of smell, then they could maybe start competing with human level mathematicians.
So this is a hard question, but not competing, but collaborating.
Yeah,
If okay, hypothetical, if I gave you an oracle that was able to do some aspect of what you do and you could just collaborate with it,
yeah. No.
what would you like that oracle to be able to do? Would you like it to maybe be a verifier, like check,
Mhm.
do the code smell, like you're yes,
Yeah,
Professor Tao, this is the correct, this is a promising, fruitful direction.
yeah.
Or would you like it to generate possible proofs and then you see which one is the
Hmm.
right one? Or would you like it to maybe generate different representation, totally different ways of seeing this problem?
Yeah, I think all of the above. A lot of it is we don't know how to use these tools because it's a paradigm that is not. Um, yeah, we have not had in the past assistants that are competent enough to understand complex instructions
Mhm.
that can work at massive scale, but are also unreliable. Like it's an interesting, a bit unreliable in subtle ways, whilst providing superficially good output. It's a interesting combination. I mean, you have like graduate students that you work with who are kind of like this, but not at scale. And we had previous software tools that can work at scale, but very narrow. So we have to figure out how to use. So Tim Gallagher actually, you mentioned he actually foresaw like in 2000, he was envisioning what mathematics would look like in actually 2.5 decades actually. Um, and
That's funny.
yeah, he wrote in his article like a hypothetical conversation between a mathematical assistant of the future and himself. He's trying to solve a problem, and they would have a conversation. Sometimes the human would propose an idea, and the AI would evaluate it, and sometimes the AI would propose an idea, and uh, and sometimes a competition was required, and AI would just go and say, "Okay, I've checked the 100 cases needed here," or the first you said this is true for all n. I've checked it for n up to 100, and it looks good so far. Or hang on, there's a problem at n equals 46. Yeah, so just a free form conversation where you don't know in advance where things are going to go, but just based on I think ideas get proposed on both sides, calculations get proposed on both sides. I've had conversations with AI where I say, okay, we're going to collaborate to solve this math problem, and it's a problem that I already know the solution to. So I try to prompt it. Okay, so here's the problem. I suggest using this tool, and then it'll find this lovely argument using a completely different tool, which eventually goes into the weeds and say, no, try using this. Okay, and it might start using this, and then it'll go back to the tool that I wanted to do before. And like you have to keep railroading it onto the path you want, and I could eventually force it to give the proof I wanted. But it was like herding cats.
Mhm.
And the amount of personal effort I had to take to not just sort of prompt it, but also check its output because like a lot of what it looked like is going to work. But I know there's a problem on line 17, and basically arguing with it. Like it was more exhausting than doing it unassisted. So but that's the current state of the art.
I wonder if there's a phase shift that happens to where it's no longer feels like herding cats, and maybe you'll surprise us how quickly that comes.
I believe so. So in formalization, I mentioned before that it takes 10 times longer to formalize a proof than to write it by hand. With these modern AI tools, and also just better tooling. The lean developers are doing a great job adding more and more features and making it user friendly. It's going from 9 to 8 to 7. Okay, no big deal. But one day it will drop below 1, and that's a phase shift because suddenly it makes sense when you write a paper to write it in lean first, or through a conversation with AI who's generating lean on the fly with you, and it becomes natural for journals to accept. Maybe they'll offer expedite refereeing. That, if a paper has already been formalized in lean, um, they'll just ask the referee to comment on the significance of the results and how it connects to literature, and not worry so much about the correctness because that's been certified. papers are getting longer and longer in mathematics, and like it's harder and harder to get good refereeing for the really long ones, unless they're really important. It is actually an issue, which and the formalization is coming in at just the right time for this to be
And the easier and easier it gets because of the tooling and all the other
right.
factors, then you're going to see much more like math lib will grow
Right.
potentially
Yeah.
exponentially.
Yeah. Yeah.
It's a virtuous cycle. Okay.
I mean, one phase shift of this type that happened in the past was the adoption of LaTeX. So,
Hmm.
so LaTeX is this typesetting language that all mathematicians use now. So in the past, people used all kinds of word processors and typewriters and whatever. But at some point, LaTeX became easier to use than all other competitors, and like people just switched, within a few years. Like it was just a dramatic phase shift.
It's a wild out there question, but what year? How far away are we from a AI system being a collaborator on a proof that wins the Fields Medal? So that level.
Okay. Well, it depends on the level of collaboration. I mean,
No, like it deserves to
right.
get the Fields Medal. Like so half
Okay.
and half.
Already, like I can imagine if it was a medal winning paper, having some AI assistance in writing it, just like the autocomplete alone is already. I use it like it speeds up my own writing. Um, like you can have a theorem, and you have a proof, and the proof has three cases, and I write down the proof of the first case, and the autocomplete just suggests, oh, now here's how the proof of the second case could work, and like it was exactly correct. That was great. Saved me like 5-10 minutes of typing.
But in that case, the AI system doesn't get the Fields Medal.
No. Um,
Are we talking 20 years, 50 years, 100 years? What do you think?
Okay. So I gave a prediction in print, but so by 2026, which is now next year, there will be math collaborations, with the AI. So not Fields Medal winning, but like actual research level math papers.
Like published ideas that
Yeah.
are in part generated by AI.
Maybe not the ideas, but at least some of the computations, the verifications. Yeah. I mean,
Has that already happened?
has already happened. Yeah. There are problems that were solved. By a complicated process, conversing with AI to propose things, and the human goes and tries it, and the contract doesn't work. But if I propose a different idea, it's hard to disentangle exactly. Um, there are certainly math results which could only have been accomplished because there was a human mathematician and an AI involved. Um, but it's hard to sort of disentangle credit. Um, I mean, these tools they do not replicate all the skills needed to do mathematics, but they can replicate sort of some non-trivial percentage of them,
Mhm.
30, 40%. So they can fill in gaps. Um, so uh, coding is a good example. So um, it's annoying for me to code in Python. I'm not a native, I'm not a professional programmer. But with AI, the friction cost of doing it is much reduced. So it fills in that gap for me. AI is getting quite good at literature review. I mean, there's still a problem with hallucinating, references that don't exist. But this, I think, is a solvable problem. If you train in the right way and so forth, you can and verify, using the internet. You should in a few years get to the point where you have a lemma that you need, and say, has anyone proven this lemma before? And it will do basically a fancy web search AI assistant and say, yeah, there are these 6 papers where something similar has happened. And I mean, you can ask it right now, and it will give you 6 papers, of which maybe one is legitimate and relevant, one exists but is not relevant, and 4 are hallucinated. It has a non-zero success rate right now, but there's so much garbage, the signal to noise ratio is so poor that um, it's most helpful when you already somewhat know the literature, and you just need to be prompted to be reminded of a paper that was already subconsciously in your memory.
Versus helping you discover new you were not even aware of, but is the correct citation
Yeah, that it can sometimes do, but when it does, it's buried in a list of options for which the other.
that are bad.
Yeah,
I mean, being able to automatically generate a related work section that is correct.
yeah,
That's actually a beautiful thing that might be another phase shift because it assigns credit correctly.
yeah, yeah,
It breaks you out of the silos of
yeah, yeah, yeah. No, I
thought,
mean, yeah, no, but there's a big hump to overcome right now. I mean, it's like self-driving cars.
Right.
The safety margin has to be really high.
Yeah.
for it to be feasible. So yeah, so there's a last mile problem with a lot of AI applications that they can develop tools that work 20%, 80% of the time, but it's still not good enough. Um, and in fact, even worse than good in some ways.
I mean, another way of asking the Fields Medal question is, what year do you think you'll wake up and be like real surprised? You read the headline, the news of something happened that AI did, like, real breakthrough, something. It doesn't, like Fields Medal, or even hypothesis. It could be like really just this alpha zero moment would go, that kind
Right,
of thing.
right. Yeah, this decade, I can see it like making a conjecture between two things that people thought was unrelated.
Oh, interesting. Generating a conjecture that's a beautiful conjecture.
Yeah, and actually has a real chance of being correct and meaningful. And
Because that's actually kind of doable, I suppose. But where the data is, yeah.
yeah,
No, that would be
well,
truly
it's
amazing. Yeah.
the current models struggle a lot. I mean, so a version of this is, I mean, the physicists have a dream of getting the AI to discover new laws of physics.
Mm.
Um, the dream is you just feed it all this data, okay, and this is here's a new pattern that we didn't see before. But it actually even struggles. The current state of the art even struggles to discover old laws of physics from the data. I mean, uh, or if it does, there's a big concern of contamination that it did it only because like somewhere in its training data it already somehow knew, Boyle's law or whatever law that you're trying to reconstruct. Um, Part of it is that we don't have the right type of training data for this. Yeah, so for laws of physics, like we don't have like a million different universes with a million different laws of nature. um, and like a lot of what we're missing in math is actually the negative space of. So we have published things that people have been able to prove, and conjectures that ended up being verified, or maybe counterexamples produced. But um, we don't have data on things that were proposed, and they're kind of a good thing to try. But then people quickly realized that it was the wrong conjecture, and then they said, "Oh, but we should actually change our claim to modify it in this way to actually make it more plausible." Um, there's a trial and error process, which is a real integral part of human mathematical discovery, which we don't record because it's embarrassing. We make mistakes, and we only like to publish our wins. Um, and the AI has no access to this data to train on. I sometimes joke that basically AI has to go through a grad school and actually, go to grad courses, do the assignments, go to office hours, make mistakes, um, get advice on how to correct the mistakes, and learn from that.
Let me ask you, if I may, about Grigori Perlman.
Hmm.
You mentioned that you try to be careful in your work and not let a problem completely consume you. Just you really fall in love with the problem and really cannot rest until you solve it. But you also hasted to add that sometimes this approach actually can be very successful.
Hmm.
An example you gave is Grigori Perelman, who proved the Poincare conjecture and did so by working alone for 7 years with basically little contact with the outside world. Can you explain this one Millennium Prize problem that's been solved, Poincare conjecture, and maybe speak to the journey that Grigori Perelman's been on?
All right, so it's a question about curved spaces. Earth is a good example. So Earth, you can think of as a 2D surface. Interesting around you, it could maybe be a torus with a hole in it, or it can have many holes. And there are many different topologies a priori that a surface could have, even if you assume that it's bounded and smooth and so forth. So we have figured out how to classify surfaces. As a first approximation, everything's determined by something called the genus, how many holes it has. So a sphere has genus 0, a donut has genus 1, and so forth. And one way you can tell these surfaces apart, probably the sphere has, which is called simply connected. If you take any closed loop on the sphere, like a big closed loop rope, you can contract it to a point and while staying on the surface. And the sphere has this property, but a torus doesn't. If you're on a torus and you take a rope that goes around, say, the outer diameter of
Hmm.
torus, there's no way, it can't get through the hole. There's no way to contract it to a point. So it turns out that the sphere is the only surface with this property of contractibility. I mean, up to like continuous deformations of the sphere. So things that are what are called topologically equivalent of the sphere. So Poincare asked the same question in higher dimensions. So it becomes hard to visualize because surface you can think of as embedded in 3 dimensions, but a curved free space, we don't have good intuition of 4D space to live it. And then there are also 3D spaces that can't even fit into 4 dimensions. You need 5 or 6 or
Mm.
higher. But anyway, mathematically, you can still pose this question that if you have a bounded 3 dimensional space now, which is also has this simply connected property that every loop can be contracted, can you turn it into a 3 dimensional version of a sphere? And so this is the Poincare conjecture. Weirdly, in higher dimensions, 4 and 5, it was actually easier. So it was solved first in higher dimensions. There's somehow more room to do the deformation. It's easier to move things around to be a sphere. But 3 was really hard. So people tried many approaches. There's sort of combinatorial approaches where you chop up the surface into little triangles or tetrahedra, and you just try to argue based on how the faces interact with each other. Um, there were um, algebraic approaches. There's various algebraic objects, like things called the fundamental group that you can attach to these homology and cohomology and all these very fancy tools. They also didn't quite work. Um, but Richard Hamilton's proposed a partial differential equations approach. So you take you take so the problem is that you have this object which is sort of secretly is a sphere, but it's given to you in a really um, in a weird way. So it's like I think of a ball that's been kind of crumpled up and twisted, and it's not obvious that it's a ball. Um, but like if you have some sort of surface which is a deformed sphere, you could for example, think of it as the surface of a balloon. You could try to inflate it. You blow it up, and naturally, as you fill it with air, the wrinkles will sort of smooth out, and it will turn into a nice round sphere. Unless, of course, it was a torus or something, in which case it would get stuck at some point. Like if you inflate a torus, there'll be a point in the middle. When the inner ring shrinks to zero, you get a singularity, and you can't blow up any further. You can't flow any further. So he created this flow, which is now called Ricci flow, which is a way of taking an arbitrary surface or space and smoothing it out to make it rounder and rounder, to make it look like a sphere. And he wanted to show that either this process would give you a sphere or it would create a singularity. Actually, very much like how PDEs they have global regularity or finite time blow up. Like it basically it's almost exactly the same thing. It's all connected. Um, and he showed that for 2 dimensional surfaces, if you started simply connected, no singularities ever formed. You never ran into trouble, and you could flow, and it will give you a sphere.
Mm.
And so he got a new proof of the 2 dimensional result.
But by the way, that's a beautiful explanation of Ricci flow and its application in this context. How difficult is the mathematics here, like for the 2D case? Is it?
Yeah, these are quite sophisticated equations on par with the Einstein equations.
Yeah.
Slightly simpler, but um, yeah, but they were considered hard nonlinear equations to solve. Um, and there's lots of special tricks in 2D that helped. But in 3D, the problem was that this equation was actually supercritical. It has the same problem as Navier-Stokes. As you blow up, maybe the curvature could get concentrated in finer, smaller, smaller regions, and it looked more and more nonlinear, and things just looked worse and worse. And there could be all kinds of singularities that showed up. Some singularities, like if there's these things called neck pinches, where the surface sort of behaves like a barbell, and it pinches at a point. Some singularities are simple enough that you can sort of see what to do next. You just make a snip, and then you can turn one surface into two and evolve them separately. But there was the prospect that there's some really nasty, like knotted singularities showed up that you couldn't see how to resolve in any way, that you couldn't do any surgery to. So you need to classify all the singularities, like what are all the possible ways that things can go wrong. Um, so what Perlman did was, first of all, he made the problem, he turned the problem from a supercritical problem to a critical problem. Um, I said before about how the invention of energy, the Hamiltonian, like really clarified um, Newtonian mechanics. Um, so he introduced something which is now called Perelman's reduced volume and Perelman's entropy. He introduced new quantities, kind of like energy, that look the same at every single scale, and turned the problem into a critical one where the nonlinearities actually suddenly looked a lot less scary than they did before. And then he still had to analyze the singularities of this critical problem. And that itself was a problem similar to this wave map thing I worked on, actually. So on the level of difficulty of that, so he managed to classify all the singularities of this problem and show how to apply surgery to each of these, and through that was able to resolve the Poincare conjecture. So um, quite like a lot of really ambitious steps, and like nothing that a large language model today, for example, could. I mean, at best, I could imagine a model proposing this idea as one of hundreds of different things to try. But the other 99 would be complete dead ends, but you'd only find out after months of work. He must have had some sense that this was the right track to pursue because, it takes years to get from A to B.
So you've done, like you said, actually, you see, even strictly mathematically, but more broadly in terms of the process, you've done similarly difficult things. What can you infer from the process he was going through? Because he was doing it alone. What are some low points in a process like that when you start to like? You've mentioned hardship, like AI doesn't know when it's
Yeah,
failing. What happens to you? You're sitting in your office when you realize the thing you did for the last few days, maybe weeks,
yeah.
is a failure.
Well, for me, I switched to a different problem. As I said, I'm a fox. I'm not a hedgehog.
But you legitimately, that is a break that you can take is to step away and look at a
Yeah,
different problem.
yeah. You can modify the problem too. Yeah, you can add some cheat. If there's a specific thing that's blocking you, that this um, some bad case keeps showing up that for which your tool doesn't work, you can just assume by fiat this bad case doesn't occur. So you do some magical thinking. Um, for the but strategically, okay, for the point to see if the rest of the argument goes through. If there's multiple problems with your approach, then maybe you just give up. Okay, but
Mhm.
if this is the only problem that and everything else checks out, then it's still worth fighting. Um, so yeah, you have to do some sort of forward reconnaissance sometimes to uh, you know
And that is sometimes productive to assume like, okay, we'll figure it out
Oh yeah, yeah,
eventually.
yeah. Sometimes actually, it's even productive to make mistakes. So one of the, I mean, there was a project which actually we won some prizes for. Actually, but with four other people, we worked on this PDE problem. Again, actually, this blow-off regularity type problem, and it was considered very hard. Jean Bourgain, who was another field methodist, who worked on a special case of this, but he could not solve the general case. Um, and we worked on this problem for 2 months, and we thought we solved it. We had this cute argument that everything fit, and we were excited. We were planning celebrationary to all get together and have champagne or something. And we started writing it up. And one of us, not me actually, but another co-author, said, "Oh, in this lemma here, we have to estimate these 13 terms that show up in this expansion. And we estimate 12 of them, but in our notes, I can't find the estimation of the 13th. Can someone supply that?" And I said, "Sure, I'll look at this." And actually, yeah, we didn't cover it. We completely omitted this term. And this term turned out to be worse than the other 12 terms put together.
Mhm.
In fact, we could not estimate this term. And we tried for a few more months and all different permutations. And there was always this one term that we could not control. And so, this was very frustrating. Um, but because we had already invested months and months of effort in this already, we stuck at this. We tried increasingly desperate things and crazy things. And after 2 years, we found an approach which was actually somewhat different, but quite a bit from our initial strategy, which didn't generate these problematic terms and actually solve the problem. So we solved the problem after 2 years. But if we hadn't had that initial false dawn of nearly solving the problem, we would have given up by month two or something and worked on an easier problem. Um, yeah, if we had known it would take 2 years, not sure we would have started the project. Yeah, sometimes actually having the incorrect, it's like Columbus traveling to New World. They had an incorrect version of the measurement of the size of the Earth. He thought he was going to find a new trade route to India. Or at least that was how he sold it in his prospectus. I mean, it could be that he actually secretly knew, but
Just on the psychological element, do you have like emotional or like self doubt that just overwhelms you moments like that? You know, because this stuff, it feels like math. Is so engrossing that like it can break you when you like invest so much yourself in the problem, and then it turns out wrong. You could start to similar way chess has broken some people.
yeah, I think different mathematicians have different levels of emotional investment in what they do. I mean, I think for some people it's just a job. You have a problem, and if it doesn't work out, you go on the next one. Um, yeah, so the fact that you can always move on to another problem, it reduces the emotional connection. I mean, there are cases, so there are certain problems that are what are called mathematical diseases, where just latch on to that one problem and they spend years and years thinking about nothing but that one problem. And maybe the career suffers and so forth. They say, "Oh, but okay, this big win. This will, once I finish this problem, I will make up for all the years of of lost opportunity. And that's. I mean, occasionally it works, but I really don't recommend it for people without the right fortitude. Yeah, so I've never been super invested in any one problem. One thing that helps is that we don't need to call our problems in advance. Well, when we do grant proposals, we sometimes say we will study this set of problems, but even there, we don't promise definitely by 5 years I will supply a proof of all these things. Um, you promise to make some progress or discover some interesting phenomena, and maybe you don't solve the problem, but you find some related problem that you can say something new about, and that's a much more feasible task.
But I'm sure for you there's problems like this. You have um, made so much progress towards the hardest problems in the history of mathematics. So is there a problem that just haunts you? It sits there in the dark corners, twin prime conjecture, Riemann hypothesis, Goldbach conjecture.
Twin prime, that sounds well. Again, so I mean, the problems like the Riemann hypothesis, those are so far out of reach.
Oh, you think so?
Yeah, there's no even viable strategy. Like even if I activate all the cheats that I know of in this problem, like there's just still no way to get from A to B.
Yeah.
Like it's um, I think it needs a breakthrough in another area of mathematics to happen first, and for someone to recognize that that would be a useful thing to transport into this problem.
So we should maybe step back for a little bit and just talk about prime numbers.
Okay.
So they're often referred to as the atoms of mathematics. Can you just speak to the structure that these atoms
So
provide?
the natural numbers have two basic operations attached to them: addition and multiplication. So if you want to generate the natural numbers, you can do one of two things. You can just start with one and add one to itself over and over again, and that generates you the natural numbers. So additively, they're very easy to generate: one, two, three, four, five. Or you can take the prime number. If you want to generate multiplicatively, you can take all the prime numbers, 2, 3, 5, 7, and multiply them all together. And together, that gives you all the natural numbers, except maybe for one. So there are these two separate ways of thinking about the natural numbers from an additive point of view and a multiplicative point of view. And separately, they're not so bad. So, like any question about that natural numbers that only was addition is relatively easy to solve, and any question that only was multiplication is relatively easy to solve. Um, but what has been frustrating is that you combine the two together, um, and suddenly you get this extremely rich. I mean, we know that there are statements in number theory that are actually as undecidable. There are certain polynomials in some number of variables. Is there a solution in the natural numbers? And the answer depends on an undecidable statement, like whether the axioms of mathematics are consistent or not. Um, but yeah, but even the simplest problems that combine something multiplicative, such as the primes, with something additive, such as shifting by two, uh, separately, we understand both of them well, but if you ask when you shift the prime by two, can you get a how often can you get another prime? We It's been amazingly hard to relate the two.
And we should say that the twin prime conjecture is just that. It posits that there are infinitely many pairs of prime numbers that differ by two.
Yes.
Now, the interesting thing is that you have been very successful at pushing forward the field in answering these complicated questions uh, of this variety. Like you mentioned, the green tile theorem. It proves that prime numbers contain arithmetic progressions of any length,
Right.
which is mind blowing that you can prove something like that.
Right. Yeah. So what we've realized because of this type of research is that there's different patterns have different levels of indestructibility. Um, so what makes the twin prime problem hard is that if you take all the primes in the world, 3, 5, 7, 11, so forth, there are some twins in there. 11 and 13 is a twin prime, pair of twin primes and so forth. But you could easily, if you wanted to, um, redact the primes to get rid of these twins. Like the twins, they show up, and there are infinitely many of them, but they're actually reasonably sparse. Not there's not. I mean, initially there's quite a few, but once you got to the millions, the trillions, they become rarer and rarer. And you could actually just, like if someone was given access to the database of primes, you just edit out a few primes here and there, they could make the twin prime conjecture false by just removing like 0.01% of the primes or something.
Mm.
Just well chosen to do this. And so you could present a censored database of the primes, which passes all of the statistical tests of the primes. That it obeys things like the prime number theorem and other things about the primes, but doesn't contain any twin primes anymore. And this is a real obstacle for the twin prime conjecture. It means that any proof strategy to actually find twin primes in the actual primes must fail when applied to these slightly edited primes. And so it must use some very subtle, delicate feature of the primes that you can't just get from like aggregate statistical analysis.
Okay, so that's out.
Yeah. On the other hand, arithmetic progressions has turned out to be much more robust. Like you can take the primes and you can eliminate 99% of the primes, actually. And you can take any 90% you want. And it turns out, and another thing we proved is that you still get arithmetic progressions.
Length
Yes.
though.
Yes.
That's crazy. I
Yeah.
mean, so this for people who don't know, arithmetic progressions is a sequence of numbers that differ by some fixed amount.
Yeah. But it's again like it's an infinite monkey type phenomenon. For any fixed length of your set, you don't get arbitrary length progressions. You only get quite short progressions.
But you're saying twin prime is not an infinite monkey
N-
phenomena. I mean, it's
No,
a very subtle monk. It's still an infinite monkey
right.
phenomenon.
Yeah. If the primes were really genuinely random, if the primes were generated by monkeys, then yes, in fact, the infinite monkey theorem would.
Oh, but you're saying that twin prime is it doesn't you can't use the same tools like it doesn't appear random almost.
Well, we don't know. Yeah, we believe the primes behave like a random set, and so the reason why we care about the Trimheim conjecture is a test case for whether we can genuinely, confidently say with 0% chance of error that the primes behave like a random set. Okay, random versions of the primes we know contain twins, at least with 100% probability, or probably tending to 100% as you go out further and further. Um, yeah, so the primes we believe that they're random. The reason why arithmetic progressions are indestructible is that regardless of whether your set looks random or looks structured, like periodic, in both cases, arithmetic progressions appear, but for different reasons. And this is basically all the ways in which the theorems, there are many proofs of these sort of arithmetic progression type theorems, and they're all proven by some sort of dichotomy where your set is either structured or random, and in both cases, you can say something, and then you put the two together. Um, but in twin primes, if the primes are random, then you're happy, you win. But if your primes are structured, they could be structured in a specific way with lizards.
Yeah.
Right. You may have encountered this kind of phenomenon. Yeah. So,
Yes.
so like a pure like there's almost no way to definitively rule out a conspiracy, and the same is true in mathematics. That a conspiracy that is to- solely devoted to eliminating twin primes, like you would have to also infiltrate other areas of mathematics to sort of, but like it could be made consistent at least as far as we know. But there's a weird phenomenon that you can make conspiracy rule out other conspiracies. So if the
Hmm.
if the world is run by lizards, it can't also be run by aliens.
Right. Right.
So one unreasonable thing is hard to disprove, but more than one, there are tools. So yeah, so for example, we know there's infinitely many primes that are no two of which are so the infinite pairs of primes which differ by at most 246 actually is the current
Oh,
record.
so there's like a bound
Yes,
on the
right. So like there's twin primes, there's this thing called cousin primes that differ by four. There's this thing called sexy primes that differ by six.
what
And
are sexy primes?
primes that differ by six.
Got it.
The name is much less, the concept is much less exciting than the name suggests.
Got it. Okay.
Um, so you can make a conspiracy rule out one of these, but like once you have like 50 of them, it turns out that you can't rule out all of them at once. It requires too much energy somehow in this conspiracy space.
How do you do the bound part? How do you
Uh,
develop a bound for the difference between the primes
okay, so
that there's an infinite number of?
it's ultimately based on what's called the pigeonhole principle. So the pigeonhole principle is a statement that if you have a number of pigeons and they all have to go into pigeonholes, and you have more pigeons than pigeonholes, then one of the pigeonholes has to have at least two pigeons in it. So there has to be two pigeons that are close together. So, for instance, if you have 100 numbers and they all range from 1 to 1,000, um, two of them have to be at most 10 apart
Hmm.
because you can divide up the numbers from 1 to 100 into 100 pigeon holes. Let's say if you have 100, if you have 101 numbers. If you have 101 numbers, then two of them have to be distance less than 10 apart because two of them have to belong to the same pigeonhole. So it's a um, basic feature of a basic principle in mathematics. Um, so it doesn't quite work with the primes directly because the primes get sparser and sparser as you go out. That fewer and fewer numbers are prime. But it turns out that there's a way to assign weights to to numbers. So there are numbers that are kind of almost prime, but they're not. They don't have no factors at all other than themselves and one, but they have very few factors. Um, and it turns out that we understand almost primes a lot better than we understand primes. Um, And so, for example, it was known for a long time that there were twin almost primes. This has been worked out. So almost primes are something we can't understand. So you can actually restrict attention to a suitable set of almost primes. And uh, whereas the primes are very sparse overall, relative to the almost primes, they actually are much less sparse. You can set up a set of almost primes where the primes have density like say 1%. And that gives you a shot at proving by applying some sort of original principle that there's pairs of primes that are just only 100 apart. But in order to prove the twin prime conjecture, you need to get the density of primes inside the almost primes up to a threshold of 50%. Once you get up to 50%, you would get twin primes. But unfortunately, there are barriers. We know that no matter what kind of good set of almost primes you pick, the density of primes can never get above 50%. It's called the parity barrier. And I would love to find, yeah, so one of my long-term dreams is to find a way to breach that barrier because it would open up not only the twin prime conjecture, but the Goldbach conjecture, and many other problems in number theory are currently blocked because our current techniques would require going beyond this theoretical parity barrier. It's like going faster than the speed of light.
Yeah, so we should say twin prime conjecture, one of the biggest problems in the history of mathematics. Goldbach conjecture also. They feel like next door neighbors. Has there been days when you felt you saw the path?
Oh yeah, yeah. Sometimes you try something and it works super well. You again the sense of mathematical smell we talked about earlier. You learn from experience when things are going too well
Yeah.
because there are certain difficulties that you sort of have to encounter. Um, I think the way a colleague might put it is that like if you are on the streets of New York and you put on a blindfold and you put in a car and after some hours the blindfold is off and you're in Beijing. Um, I mean that was too easy somehow. Like
Yeah.
there was no ocean being crossed. Even if you don't know exactly what was done, you're suspecting that something wasn't right.
But is that still in the back of your head to do you return to these to the
Um,
prime do you return to the prime numbers every once in a while to see?
Yeah, when I have nothing better to do, which is less and less now, time, which is I get busy with so many things these days. But yeah, when I have free time and I'm too frustrated to work on my sort of real research projects, and I also don't want to do my administrative stuff, or I don't want to do some errand for my family. Um, I can play with these things for fun, and usually you get nowhere. Yeah, you have to learn to just say, okay, fine. Once again, nothing happened. I will move on. Yeah, very occasionally, one of these problems I actually solved. Well, sometimes, as you say, you think you solved it, and then you forward for maybe 15 minutes, and then you think I should check this because this is too easy, too good to be true, and it usually is.
What's your gut say about when these problems would be solved? Twin
Um,
prime and Goldbach.
Prime, I think we'll
10
keep getting
years?
keep getting more partial results. It does need at least one. This parity barrier is the biggest remaining obstacle. There are simpler versions of the conjecture where we are getting really close. Um, So I think we will, in 10 years, we will have many more, much closer results. We may not have the whole thing. Yeah, so twin primes is somewhat close. Riemann hypothesis, I have no, I mean, it has to happen by accident. I think,
So the Riemann hypothesis is a kind of more general conjecture about the distribution of prime numbers, right?
right. Yeah, it's states are sort of viewed multiplicatively. Like for questions only involving multiplication, no addition, the primes really do behave as randomly as you could hope. So there's a phenomenon in probability called square root cancellation that like if you want to poll, say, America on some issue, and you ask one or two voters, and you may have sampled a bad sample, and then you get a really imprecise measurement of the full average. But if you sample more and more people, the accuracy gets better and better, and the accuracy improves like the square root of the number of people you sampled. So yeah, if you sample 1,000 people, you can get like a 2-3% margin of error. So, in the same sense, if you measure the primes in a certain multiplicative sense, there's a certain type of statistic you can measure, and it's called the Riemann zeta function, and it fluctuates up and down. But in some sense, as you keep averaging more and more, if you sample more and more, the fluctuations should go down as if they were random. And there's a very precise way to quantify that, and the Riemann hypothesis is a very elegant way that captures this. But as with many other areas in mathematics, we have very few tools to show that something really genuinely behaves like really random. And this is actually not just a little bit random, but it's asking that it behaves as random as an actually random set. This square root cancellation. And we know actually because of things related to the parity problem actually that most of us usual techniques cannot hope to settle this question. The proof has to come out of left field. Um, yeah, but what that is, yeah, no one has any serious proposal. Yeah, and there's various ways to sort of, as I said, you can modify the primes a little bit, and you can destroy the Riemann hypothesis. So, like, it has to be very delicate. You can't apply something that has huge margins of error. It has to just barely work. And like, there's like all these pitfalls that you have to like dodge very adeptly.
The prime numbers is just fascinating.
Yeah, yeah, yeah.
What to you is most mysterious about the prime numbers?
That's a good question. So, like, conjecturally, we have a good model of them. I mean, like, as I said, I mean, they have certain patterns, like the primes are usually odd, for instance. But apart from these sort of obvious patterns, they behave very randomly. And just assuming that they behave, so there's something called the Kramer random model of the primes, that after a certain point, primes just behave like a random set. And there's various slight modifications to this model, but this has been a very good model. It matches the numerics. It tells us what to predict. Like I can tell you with complete certainty the Trinity conjecture is true. The random model gives overwhelming odds it is true. I just can't prove it. Most of our mathematics is optimized for solving things with patterns in them. Um, and the primes have this anti-pattern, um, as do almost everything, really. But we can't prove that. Yeah, I guess it's not mysterious that the primes be it's kind of random because there's sort of no reason for them um, uh, to have any kind of secret pattern. But what is mysterious is what is the mechanism that really forces the randomness to happen. And this is just absent.
Another incredibly surprisingly difficult problem is the Collatz conjecture.
Oh, yes.
Simple to state,
Hmm.
beautiful to visualize in
Yes.
its simplicity, and yet extremely difficult to solve. And yet you have been able to make progress. Paul Erdar said about the Collatz conjecture that mathematics may not be ready for such problems.
Right.
Others have stated that it is an extraordinarily difficult problem, completely out of reach. This is in 2010, out of reach of present day mathematics, and yet
Yeah.
you have made some progress. Why is it so difficult to make? Can you actually even explain what it is?
Oh,
It's
yeah,
easy
yeah.
to.
So it's a problem that you can explain. Yeah, it helps with some visual aids, but yeah. So you take any natural number, like say 13, and you apply the following procedure to it. So if it's even, you divide it by 2. And if it's odd, you multiply it by 3 and add 1. So even numbers get smaller, odd numbers get bigger. So 13 will become 40 because 13 times 3 is 39. Add 1, you get 40. So it's a simple process. For odd numbers and even numbers, they're both very easy operations. And then you put them together, it's still reasonably simple. But then you ask what happens when you iterate it. You take the output that you just got and feed it back in. So 13 becomes 40. 40 is now even. Divide by 2 is 20. 20 is still even. Divide by 2, 10. 5. And then 5 times 3 plus 1 is 16. And then 8, 4, 2, 1. So, and then from 1, it goes 1, 4, 2, 1, 4, 2, 1. It cycles forever. So this sequence I just described, 13, 40, 20, 10, and so forth, these are also called hailstone sequences because there's an oversimplified model of hailstone formation, which is not actually quite correct, but it's so somehow taught to high school students as a first approximation. Is that like a little nugget of ice gets a nice crystal forms in a cloud, and it goes up and down because of the wind, and sometimes when it's cold, it acquires a bit more mass, and maybe it melts a little bit. And this process of going up and down creates this sort of partially melted ice, which eventually creates this hailstone, and eventually it falls down to the earth. So the conjecture is that no matter how high you start up, like you take a number which is in the millions or billions, you have this process that goes up if you're odd and down if you're even. It eventually goes down to Earth all the time.
No matter where you start with this very simple algorithm, you end up at one,
Right.
and you might climb for a while
Right. Yeah. So
come down.
yeah. If you plot it, these sequences, they look like Brownian motion. They look like the stock market. They just go up and down in a seemingly random pattern. And in fact, usually that's what happens. That if you plug in a random number, you can actually prove, at least initially, that it would look like random walk. And that's actually a random walk with a downward drift. It's like if you're always gambling on a roulette at the casino with odds slightly weighted against you. So sometimes you win, sometimes you lose, but over in the long run, you lose a bit more than you win. And so normally your wallet will go to zero if you just keep playing over and over again.
So statistically, it makes sense that it
Yes,
would
yeah.
go
So,
down.
so the result that I proved, roughly speaking, is such that statistically, like 99% of all inputs would drift down to maybe not all the way to one, but to be much smaller than what you started. So, it's like if I told you that if you go to a casino, most of the time you end up, if you keep playing it for long enough, you end up with a smaller amount in your wallet than when you started. That's kind of like what the result that I proved.
So why is that result like? Can you continue down that thread to prove the full conjecture?
Well, the problem is that I used arguments from probability theory, and there's always this exceptional event. So so in probability we have this law of large numbers, which tells you things like if you play a casino with a game at a casino with a losing expectation, over time you are guaranteed, well, almost surely, with probability as close to 100% as you wish, you're guaranteed to lose money. But there's always this exceptional outlier. Like it is mathematically possible that even when the game is the odds are not in your favor, you could just keep winning slightly more often than you lose. Very much like how in Navier-Stokes, it could be, most of the time your waves can disperse. There could be just one outlier choice of initial conditions that would lead you to blow up. And there could be one outlier choice of um, a special number that you stick in that shoots off to infinity, while all other numbers crash to Earth, crash to one.
Yeah.
Um, in fact, there's some mathematicians who've Alex Kantorovich, for instance, who've proposed that that actually these Collatz iterations are like these cellular automata. Actually, if you look at what they happen in binary, they do actually look a little bit like these game of life type patterns.
Hmm.
And in an analogy to how the game of life can create these massive like self-replicating objects and so forth, possibly you could create some sort of heavier than air flying machine, a number which is actually encoding this machine, which is just whose job it is to encode, is to create a version of itself which is larger.
Heavier than air machine encoded in a number
Yeah,
that flies forever.
yeah. So Conway, in fact, worked on this problem as well.
Oh wow.
So Conway, so similar. In fact, that was one of the inspirations for the Navier-Stokes project. Conway studied generalizations of the collapse problem, where instead of multiplying by 3 and adding 1 or dividing by 2, you have a more complicated branching rules. But instead of having 2 cases, maybe you have 17 cases and then you go up and down. And he showed that once your iteration gets complicated enough, you can actually encode Turing machines and you can actually make these problems undecidable and do things like this. In fact, he invented a programming language for these kind of fractional linear transformations. He called it FactTran as a play on Fortran. And he showed that you can you can program it was Turing complete. You could make a program that if your number you insert in was encoded as a prime, it would sync to zero. It would go down, otherwise it would go up, and things like that. So the general class of problems is really uh, as complicated as all the mathematics.
Some of the mystery of the cellular automata that we talked about, having a mathematical framework to say anything about cellular automata, maybe the same kind of framework is required
Yeah,
for
yeah,
the Clock's conjecture.
yeah. If you want to do it not statistically, but you really want 100% of all inputs to fall to Earth. Yeah. So what might be feasible is yeah, statistically 99%.
Yeah.
Go to one, but like everything, yeah, that looks hard.
What would you say is out of these within reach famous problems is the hardest problem we have today? Is the Riemann hypothesis?
Riemann is up there. P equals NP is a good one because like that's a meta problem. Like if you solve that in the positive sense that you can find a P equals NP algorithm, then potentially this solves a lot of other problems as well.
And we should mention some of the conjectures we've been talking about. A lot of stuff is built on top of them now. There's
Yeah,
ripple effects. P equals on P has more ripple effects than basically any other.
right. If the Riemann hypothesis is disproven, um, that would be a big mental shock to the number theorists, but it would have follow-on effects for cryptography. Um,
Uh-huh.
because a lot of cryptography uses number theory constructions involving primes and so forth. And it relies very much on the intuition that number theories have built over many years of what operations involving primes behave randomly and what ones don't. And in particular, our encryption methods are designed to turn text with information on it into text which is indistinguishable from random noise. So, and hence we believe to be almost impossible to crack, at least mathematically. Um, but uh, if something as core to our beliefs as the Riemann hypothesis is wrong, it means that there are actual patterns of the primes that we're not aware of. And if there's one, there's probably going to be more. Um, and suddenly, a lot of our crypto systems are in doubt. Uh,
Yeah. But then how do you then say stuff about the primes?
yeah,
Like you're going towards the Collex conjecture again. Because if you want it to be random, right? You
yes,
want it to be
yeah.
randomly.
Yeah, so more broadly, I'm just looking for more tools, more ways to show
Yeah,
that things are random. How do you prove a conspiracy doesn't happen?
right. Is there any chance to you that P equals NP? Is there some, can you imagine a possible universe?
It is possible. I mean, there's various scenarios. I mean, there's one where it is technically possible, but in practice, never actually implementable. The evidence is sort of slightly pushing in favor of no, that we probably P is not equal to NP.
I mean, it seems like it's one of those cases similar to Riemann hypothesis. I think the evidence is leaning pretty heavily on the no.
Certainly more on the no than on the yes. The funny thing about P equals NP is that we have also a lot more obstructions than we do for almost any other problem. So while there's evidence, we also have a lot of results ruling out many, many types of approaches to the problem. This is the one thing that the computer science has actually been very good at. It's actually saying that certain approaches cannot work, no-go theorems. It could be undecidable. We don't know.
There's a funny story I read that when you won the Fields Medal, somebody from the internet wrote you and asked, what are you going to do now that you've won this prestigious award? And then you just quickly, very humbly said that, this a shiny medal is not going to solve any of the problems I'm currently working on. So I'm going to
Okay.
keep, I'm going to keep working on them. It's just, first of all, it's funny to me that you would answer an email in that context. And second of all, it just shows your humility. But anyway, maybe you could speak to the Fields Medal, but it's another way for me to ask uh, about Grigori Perelman. What do you think about him famously declining the Fields Medal and the Millennium Prize, which came with a $1 million of prize money? He stated that I'm not interested in money or fame. The prize is completely irrelevant for me. If the proof is correct, then no other recognition is needed.
Yeah, no, he's somewhat of an outlier, even among mathematicians who tend to have somewhat idealistic views. I've never met him. I think I'd be interested to meet him one day, but I never had the chance. I know people who met him, but he's always had strong views about certain things. I mean, it's not like he was completely isolated from the math community. I mean, he would give talks and
Hmm.
write papers and so forth. But at some point, he just decided not to engage with the rest of the community. He was disillusioned or something. I don't know. And he decided to peace out and collect mushrooms in St. Petersburg or something, and
Hmm.
that's fine. And you can do that. I mean, that's another sort of flip side. I mean, we are not a lot of problems that we solve. Some of them do have practical application, and that's great. But like if you stop thinking about a problem, so he hasn't published since in this field, but that's fine. There's many other people who've done so as well. Um, yeah, so I guess one thing I didn't realize initially with the Fields Medal is that it sort of makes you part of the establishment. So most mathematicians, they're just career mathematicians. You just focus on publishing the next paper, maybe getting promoted one rank, and starting a few projects, maybe taking some students or something. Yeah, but then suddenly people want your opinion on things, and you have to think a little bit about things that you might just so foolishly say because no one's going to listen to you. It's more important now.
Is it constraining to you? Are you able to still have fun and be a rebel and try crazy stuff and
Well,
play with
I
ideas?
have a lot less free time than I
Yeah.
had previously. I mean, mostly by choice. I mean, I can always see I have the option to sort of decline. So I decline a lot of things. I could decline even more, or I could acquire a reputation for being so unreliable that people don't even ask anymore. Uh, this is
I love
this.
I love the different algorithms here.
Yeah,
This is great.
it's always an option. But there are things that are like I mean, I don't spend as much time as I do as a postdoc. Just working on one problem at a time or fooling around. I still do that a little bit, but yeah, as you advance in your career, the more soft skills. So math somehow front loads all the technical skills to the early stages of your career. So yeah, so it's as a postdoc, as publish or perish, you're incentivized to basically focus on proving very technical theorems to sort of prove yourself, as well as prove the theorems. But then as you get more senior, you have to start, mentoring and giving interviews, and trying to shape direction of the field both research wise and sometimes you have to do various administrative things, and it's kind of the right social contract because you need to work in the trenches to see what can help mathematicians.
The other side of the establishment, sort of the really positive thing, is that you get to be a light that's an inspiration to a lot of young mathematicians or young people that are just interested in mathematics. It's like
Yeah,
it's
yeah,
just how the human mind works. This is where I would probably say that I like the Fields Medal. That it does inspire a lot of young people somehow. I don't. This is just how human brains work.
yeah.
At the same time, I also want to give sort of respect to somebody like Grigori Perelman, who is critical of awards in his mind. Those are his principles, and any human that's able for their principles to like do the thing that most humans would not be able to do. It's
Right.
beautiful to see.
Some recognition is necessary and important, but yeah, it's also important to not let these things take over your life,
Yeah.
and like only be concerned about getting the next big award or whatever. I mean, yeah, yeah. So again, you see these people try to only solve like a really big math problems and not work on things that are less sexy, if you wish,
Mhm.
but actually still interesting and instructive. As you say, like the way the human mind works, it's we understand things better when they're attached to humans. And also, if they're attached to a small number of humans, like so, the way our humans mind is wired, we can comprehend the relationships between 10 or 20 people. But once you get beyond that, like 100 people, like there's a limit. I think there's a name for it. Beyond which it just becomes the other.
Yeah.
Um, and so you have to simplify the whole mass of 99.9% of humanity becomes the other, and and often these models are incorrect, and this causes all kinds of problems. But um, so yeah, so to humanize a subject, if you identify a small number of people and say, these are representative people of the subject, so role models, for example, um, that has some role, but it can also be uh, yeah, too much of it can be harmful because I'll be the first to say that my own career path is not that of a typical mathematician. I had a very accelerated education. I skipped a lot of classes. I think I had very fortunate mentoring opportunities, and I think I was at the right place at the right time. Just because someone doesn't have my um, trajectory, doesn't mean that they can't be good mathematicians. I mean, they may be good mathematicians in a very different style, and we need people with a different style. Um, and even if and sometimes too much focus is given on the person who does the last step to complete a project in mathematics or elsewhere that's really taken centuries or decades with lots and lots of building on lots of previous work. um, but that's a story that's difficult to tell if you're not an expert because it's easier to just say one person did this one thing. It makes for a much simpler history.
I think on the whole, it is a hugely positive thing to talk about Steve Jobs
Mm.
as a representative of Apple. When I personally know, and of course everybody knows the incredible design, the incredible engineering teams,
Mhm, mhm.
just the individual humans on those teams. They're not a team; they're individual humans on a team, and there's a lot of brilliance there. But it's just a nice shorthand, like a very like pie.
Yeah,
It's Steve Jobs
yeah, yeah.
pie.
As a starting point,
Yeah.
as a first approximation,
Yes,
that's how you
and
call
then
it.
read some biographies and then look into much deeper first approximation.
Yeah.
That's right. So you mentioned you were at Princeton to
Hmm.
Andrew Wiles at that time
Oh
was a
yeah.
professor there.
Hmm.
It's a funny moment how history is just all interconnected. And at that time, he announced that he proved the Fermat's last
Oh yes.
theorem. What did you think? Maybe looking back now with more context about that moment in math history.
Yeah, so I was a graduate student at the time. I mean, I vaguely remember, there was press attention, and we all had the same. We all had pigeonholes in the same mailroom. So we all check our mail, and like suddenly Andrew Wows's mailbox exploded to be overflowing.
That's a
Um,
good. That's a good metric.
yeah, So yeah, we all talked about it at tea and so forth. I mean, we didn't understand. Most of us sort of didn't understand the proof. We understand sort of high level details. In fact, there's an ongoing project to formalize it in Lean. Right? Kevin Buzzard is actually.
Yeah, can we take that small tangent? Is it how difficult is that? Because as I understand the Fermat's last the proof for Fermat's last theorem has like super complicated objects.
Yeah,
It's
yeah,
really difficult to formalize. No.
yeah. I guess yeah, you're right. The objects that they use, um, you can define them. So they've been defined in Lean. Okay, so just
Oh
defining
yeah.
what they are can be done. That's really not trivial, but it's been done. But there's a lot of really basic facts about these objects that have taken decades to prove, and that they're in all these different math papers. And so lots of these have to be formalized as well. Um, Kevin Buzzard's goal, actually, he has a 5-year grant to formalize Fermat's last theorem, and his aim is that he doesn't think he will be able to get all the way down to the basic axioms, but he wants to formalize it to the point where the only things that he needs to rely on as black boxes are things that were known by 1980 to number theorists at the time, um, and then some other work would have to be done to get from there. Um, so it's a different area of mathematics than the type of mathematics I'm used to. Um, in analysis, which is kind of my area, the objects we study are kind of much closer to the ground. I study things like prime numbers and functions and things that are within scope of a high school math education to at least define. Um, yeah, but then there's this very advanced algebraic side of number theory where people have been building structures upon structures for quite a while, and it's a very sturdy structure. It's been very at the base at least it's extremely well developed. There's textbooks and so forth, but it does get to the point where if you haven't taken these years of study and you want to ask about what is going on at like level 6 of this tower, you have to spend quite a bit of time before they can even get to the point where you see something you recognize.
What inspires you about his journey that was similar as we talked about? 7 years, mostly working in secret.
Yeah, yes, that is a romantic. Yeah, so it kind of fits with sort of the romantic image that I think people have of mathematicians, to the extent that they think of them at all as these kind of eccentric, wizards or something. So that certainly kind of uh, accentuated that perspective. I mean, it is a great achievement. Yeah, his style of solving problems is so different from my own, but which is great. I mean, we need
Can
people
you
like that.
speak to it? Like what
Um,
in terms of like you like the collaborative.
I like moving on from a problem if it's giving too much
Got it.
difficulty.
Got it.
But you need the people who have the tenacity and the fearlessness. I've collaborated with people like that where I want to give up because the first approach that we tried didn't work and the second one didn't approach, but they're convinced and they have the third,
Mm.
fourth, and the fifth approach works. Um, and I have to eat my words. Okay, I didn't think this was going to work, but yes, you were right all along.
And we should say for people who don't know, not only are you known for the brilliance of your work, but the incredible productivity, just the number of papers, which are all of very high quality. So there's something to be said about being able to jump from topic to topic.
Yeah, it works for me. Yeah, I mean, but there are also people who are very productive and they focus very deeply on. Yeah, I think everyone has to find their own workflow. Like one thing which is a shame in mathematics is that we have mathematics. There's sort of a one size fits all
Mm.
approach to teaching mathematics, um, and so we have a certain curriculum and so forth. I mean, maybe like if you do math competitions or something, you get a slightly different experience. But I think many people they don't find their native math language until very late, or usually too late, so they stop doing mathematics, and they have a bad experience with a teacher who's trying to teach them one way to do mathematics, and they don't like it. Um, my theory is that humans don't come. Evolution has not given us a math center of a brain directly. We have a vision center and a language center, and some other centers which have evolution has honed. But it doesn't. We don't have an innate sense of mathematics. Um, but our other centers are sophisticated enough that different people we can repurpose other areas of our brain to do mathematics. So I use the visual center to do mathematics, and so they think very visually when they do mathematics. Some people have repurposed their language center, and they think very symbolically. Um, you know, um, some people like if they are very competitive and they're like gaming, there's this part of your brain that's very good at solving puzzles and games and that can be repurposed. But like when I talk to other mathematicians, they don't quite think that I can tell that they're using somehow different styles of thinking than I am. I mean, not disjoint, but they may prefer. I don't actually prefer visual so much. I need lots of visual aids myself. Um, you know, mathematics provides a common language, so we can still talk to each other even if we are thinking in different ways.
But you can tell there's a different set of subsystems being used in the thinking
Yeah,
process.
they take different paths. They're very quick at things that I struggle with, and vice versa. And yet they still get to the same goal.
Yeah,
Um,
that's beautiful.
yeah, but I mean, the way we educate, unless you have like a personalized tutor or something, I mean, education sort of just by nature of scale has to be mass produced. You have to teach to 30 kids. And, if they have 30 different styles, you can't teach 30 different ways.
On that topic, what advice would you give to students, young students who are struggling with math and but are interested in it and would like to get better? Is there something in this
Yeah,
in this complicated educational context? What would you
yeah, it's a tricky
advise?
problem. One nice thing is that there are now lots of sources for mathematical enrichment outside the classroom.
Hmm.
So in my day, there were math competitions, and there are also like popular math books in the library.
Hmm.
But now you have YouTube. There are forums just devoted to solving math puzzles and math shows up in other places. Like for example, there are hobbyists who play poker for
Hmm.
fun, and they for very specific reasons are interested in very specific probability questions,
Yes.
they actually there's a community of amateur probabilists in poker,
Hmm.
in chess, in baseball. I mean, yeah, um, there's math all over the place. And I'm hoping actually with these new sort of tools for lean and so forth that actually we can incorporate the a broader public into math research projects. Like this is almost is doesn't happen at all currently. So in the sciences, there is some scope for citizen science, like astronomers, they're amateurs who discover comets, and there's biologists, there are people who could identify butterflies and so forth. And there are a small number of activities where amateur mathematicians can like discover new primes and so forth. But previously, because we had to verify every single contribution, like most mathematical research projects, it would not help to have input from the general public. In fact, it would just be time consuming because just error checking and everything. But one thing about these formalization projects is that they are bringing in more people. So I'm sure there are high school students who've already contributed to some of these formalizing projects who contributed
Hmm.
to Mathlib. Um, you don't need to be a PhD holder to just work on one atomic thing.
There's something about the formalization here that also, as a very first step, opens it up to the programming community too. The
Yes,
people who are already comfortable
yes,
with program. It seems like programming is somehow maybe just a feeling, but it feels more accessible to folks than math. Math
yeah.
is seen as this like extreme, especially modern mathematics, seen as this extremely difficult to enter area, and programming is not. So that could be just an entry point.
You can execute code and you can get results. You can print a
Right.
hello world pretty quickly.
Yeah.
Um, like uh, if programming was taught as an almost entirely theoretical subject, where you just taught the computer science, the theory of functions and routines and so forth, and outside of some very specialized homework assignments, you would not actually program like on the weekend for fun,
Yeah.
or yeah, they would be as considered as hard as math.
Hmm.
Um, yeah, so as I said, there are communities of non-mathematicians where they're deploying math for some very specific purpose, like optimizing their poker game, and for them, then math becomes fun for them.
What advice would you give in general to young people how to pick a career, how to find themselves, like what
Yeah,
they could be
that's
good
a
at?
that's a tough question. Yeah, so there's a lot of certainty now in the world. I mean, there was this period after the war where, at least in the West, if you came from a good demographic, uh, like there was a very stable path to a good career. You go to college, you get an education, and you pick one profession, and you stick to it. It's becoming much more a thing of the past. So I think you just have to be adaptable and flexible. I think people have to get skills that are transferable. like learning one specific programming language or one specific subject of mathematics or something. It's that itself is not a super transferable skill, but sort of knowing how to um, reason with abstract concepts or how to problem solve when things go wrong. And so anyway, these are things which I think we will still need, even as our tools get better. And you'll be working with AIs more and so forth.
But actually, you're an interesting case study. I mean, you're like one of the great living mathematicians, right? And then you had a way of doing things, and then all of a sudden you start learning. I mean, first of all, you kept learning new
Yeah,
fields, but you learn lean. That's a non-trivial thing to learn. Like
yeah,
for a lot of people, that's an extremely uncomfortable leap to take, right?
yeah.
A lot of
So
mathematicians.
um, first of all, I've always been interested in new ways to do mathematics. I feel like a lot of the ways we do things right now are inefficient. I spend like me and my colleagues, we spend a lot of time doing very routine computations or doing things that other mathematicians would instantly know how to do, and we don't know how to do them. And why can't we search and get a quick
Mm,
response and so on? So that's why I've always been interested in exploring new workflows. About 4 or 5 years ago, I was on a committee where we had to ask for ideas for interesting workshops to run at a math institute.
mhm.
And at the time, Peter Schulze had just formalized one of his new theorems, and there were some other developments in computer-assisted proof that looked quite interesting. And I said, "Oh, we should run a workshop on this. This would be a good idea." And then I was a bit too enthusiastic about this idea, so I got voluntold to actually run it. So I did with a bunch of other people, Kevin Buzzard and Jordan Ellenberg and a bunch of other people. And it was a nice success. We brought together a bunch of mathematicians and computer scientists and other people, and we got up to speed on state of the art. And it was really interesting developments that most mathematicians didn't know was going on. That lots of nice proofs of concept, just sort of hints of what was going to happen. This was just before ChatGPT, but there was one talk about language models and the potential capability of those in the future. So that got me excited about the subject. So I started giving talks about this is something more of us should start looking at. Now that I arranged to run this conference, and then ChatGPT came out, and like suddenly AI was everywhere, and so I got interviewed a lot about this topic, and in particular the interaction between AI and formal proof assistants. And I said, yeah, they should be combined. This is perfect synergy to happen here. And at some point, I realized that I have to actually do not just talk the talk, but walk the walk.
Mhm.
I don't work in machine learning, and I don't work in proof formalization. And there's a limit to how much I can just rely on authority and saying, I'm a well-known mathematician. Just trust me. When I say that this is going to change mathematics, and I'm not doing it when I don't do any of it myself. So I felt like I had to actually uh, justify it. But a lot of what I get into actually, I don't quite see in advance as how much time I'm going to spend on it, and it's only after I'm sort of waist deep in a project that I realize by that point I'm committed.
Well, that's deeply admirable that you're willing to go into the fray, be in some small way a beginner, right? Or
Yeah,
have some of the sort of challenges that a beginner would, right? It's a
yeah,
new concepts, new ways of thinking, also, sucking at a thing that others I think I think in that talk, you could be a Fields Medal winning mathematician and an undergrad knows something better than you.
yeah. I think mathematics inherently. I mean, mathematics is so huge these days that nobody knows all of modern mathematics, and inevitably we make mistakes, and you know you can't cover up your mistakes with just sort of bravado and
Yeah,
I mean, because people will ask for your proofs, and if you don't have the proofs, you don't have the proofs.
God, I love math.
Yeah, so it does keep us honest. I mean, not I mean, you can still. It's not a perfect panacea, but I think we do have more of a culture of admitting error than because we're forced to all the time.
Big ridiculous question. I'm sorry for it once again. Who is the greatest mathematician of all time? Maybe one who's no longer with us. Who are the candidates? Euler, Gauss, Newton, Ramanujan, Hilbert.
So first of all, as mentioned before, like there's some time dependence, but
On the day.
yeah, like if you plot cumulatively over time, for example, Euclid like sort of like
Yeah.
is one of the leading contenders. and then maybe some unnamed, anonymous messages before that. Whoever came up with the concept of numbers, you know,
Do mathematicians today still feel the impact of Hilbert? Just
oh yeah,
directly of what everything that's happened in the 20th century?
yeah, Hilbert spaces. We have lots of things that are named after him, of course. Just the arrangement of mathematics and just the introduction of certain concepts. I mean, 23 problems have been extremely influential.
There's some strange power to the declaring which problems
Yeah,
are hard to
yeah,
solve, the statement of the open problems.
yeah. I mean, this is bystander effect everywhere, right? Like if no one says you should do X, everyone just sort of mills around waiting for somebody else to do something, and like nothing gets done. Um, and like it's one thing that actually you have to teach undergraduates in mathematics is that you should always try something. So you see a lot of paralysis in an undergraduate trying a math problem. If they recognize that there's a certain technique that can be applied, they will try it. But there are problems for which they see none of their standard techniques obviously applies. And the common reaction is then just paralysis. I don't know what to do. I think there's a quote from The Simpsons. I've tried nothing and I'm all out of ideas. Um, so, like the next step then is to try anything, like no matter how stupid. And
Mhm.
in fact, almost the stupider the better. Um, which, I want a technique which is almost guaranteed to fail, but the way it fails is going to be instructive. Like it fails because you're not at all taking into account this hypothesis. Oh, this hypothesis must be useful. That's a clue.
I think you also suggested somewhere this fascinating approach, which really stuck with me. And I started using it, and it really works. I think you said it's called structured procrastination.
No, yes, yeah.
It's when you really don't want to do a thing, that you imagine a thing you don't want to do more
Yes, yes,
that's
yes.
worse than that, and then in that way you procrastinate by not doing the thing that's worse.
Yeah, yeah,
It's a nice hack. It actually works.
yeah, yeah. I mean, with anything, like, I mean, like, psychology is really important. Like you talk to athletes like marathon runners and so forth, and and they talk about what's the most important thing is it their training regimen or the diet and so forth. Actually, so much of it is actually psychology.
Mhm.
Just tricking yourself to think that the problem is feasible, so that you're motivated to do it.
Is there something our human mind will never be able to comprehend?
Well, I sort of, I guess, a mathematician. I mean, like it's by induction. It's sufficient. There must be some sufficient large number that we can't understand. That was the first thing that came to mind.
So that, but even broadly, is there something about our mind that's we're going to be limited even with the help of mathematics?
Well, okay. I mean, it's like how much augmentation are you willing? Like for example, if I didn't even have pen and paper, um, like if I had no technology whatsoever, okay, so I'm not allowed blackboard, pen and paper,
Right. You're already much more limited than you would be.
incredibly limited. Even language, the English language is a technology. Uh, it's it's one that's been very internalized.
So you're right. There really the formulation of the problem is incorrect because there really is no longer a just a solo human. We're already augmented in extremely complicated, intricate ways,
Yeah,
right?
yeah, yeah.
So we're already like a collective intelligence.
Yes, yeah, yes. So humanity plural has much more intelligence in principle on its good days than the individual humans put together. It can also have
Yeah.
less. Okay, but um, yeah. So yeah, the mathematical community plural is an incredibly super intelligent uh, entity. Um, that no single human mathematician can come close to replicating. You see it a little bit on these like question analysis sites. So this Math Overflow, which is the math version of Stack Overflow,
Mhm.
and like sometimes you get like this very quick responses to very difficult questions from the community, and it's a pleasure to watch actually as an expert.
I'm a fan spectator of that of that site, just seeing the brilliance of the different people, the depth of knowledge that some people have, and the willingness to engage in the rigor and the nuance of the particular question. It's pretty cool to watch. It's
Yeah,
fun. It's almost like just fun to
yeah.
watch. What gives you hope about this whole thing we have going on, human civilization?
I think the younger generation is always like really creative and enthusiastic and inventive. It's a pleasure working with young students. You know, the uh, the progress of science tells us that the problems that used to be really difficult can become extremely, can become like trivial to solve. You know, and I mean, like it was like navigation. Just knowing where you were on the planet was this horrendous problem. People died. Um, or lost fortunes because they couldn't navigate. And we have devices in our pockets that do this automatically for us. Like it's a completely solved problem. So things that are seem unfeasible for us now could be maybe just sort of homework exercises for me. Mhm.
Yeah, one of the things I find really sad about the finiteness of life is that I won't get to see all the cool things we create as a civilization, you know? That because in the next 100 years, 200 years, just imagine showing up in 200 years.
Yeah, well, already plenty has happened. Like if you could go back in time and talk to your teenage self or something, what I mean,
Yeah.
and just the internet and now AI. I mean, it's like again, they're beginning to be internalized and says, yeah, of course, an AI can understand our voice and give reasonable, slightly incorrect answers to any question. But this was mind blowing even 2 years ago.
And in the moment, it's hilarious to watch on the internet and so on. The drama, people take everything for granted very quickly, and then we humans seem to entertain ourselves with drama. Well, out of anything that's created, somebody needs to take one opinion, another person needs to take an opposite opinion, argue with each other about it. But when you look at the arc of things, I mean, it's just even in progress of robotics,
Yeah,
just to take a step back and be like, wow, this is beautiful that we humans are able to create this.
yeah. When the infrastructure and the culture is healthy, the community of humans can be so much more intelligent and mature and rational than the individuals within it.
The following is a conversation with Oliver Anthony, singer songwriter from Virginia, who first gained worldwide fame. The following is a conversation with Jennifer Burns, a historian of ideas, including the evolution of economic, political, and social ideas in the United States in the 20th century to today. She wrote two biographies, one on Milton Friedman and the other on Ayn Rand, both of which I highly recommend. This was a super technical and super fascinating conversation. At the end, I make a few comments about my previous conversation with President Zelensky for those of you who may be interested. This is a Lex Friedman podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Jennifer Burns. You have written two biographies, one on Milton Friedman and one on Ayn Rand. So, if we can, we will focus on each one separately. But first, let's talk about the ideas the two of them held in common: the value of individual freedom, skepticism of collectivism, and the ethics of capitalism. Can you talk about the big picture ideas they converge on?
Yeah. So Milton Friedman and Ayn Rand, in the biggest picture, they're both individualists and they're skeptical of collectivities and collectivism. So their unit of analysis is the individual, what's good for the individual, what works for the individual, and their understanding of society kind of flows from that. They also both use this focus on individualism to justify and to support capitalism as a social and economic system. So we can put them in a similar category. We can call them individualists. We could call them libertarians of a sort. But they're also really different in how they approach capitalism, how they approach thinking. Ayn Rand developed her own moral and philosophical system to justify individualism and to connect the individual to capitalism and to support capitalism as a social and economic system. Friedman struggles a bit more with how to justify capitalism, and he'll ultimately come down to freedom as his core value, like his God, as he says. And so freedom does connect back to the individual, but he's not justifying capitalism for its own sake. He's justifying it for its ability to underwrite freedom in a social sense and also in the individual sense.
At a high level, are there interesting differences between them? You already mentioned a few, maybe in terms of who they are personally, maybe in terms of how they approach the justification for capitalism, maybe other ways.
Yeah, for sure. So beyond this idea that Milton Friedman takes a while to come to his justification of capitalism, whereas Ayn Rand kind of has it from the start. She really focuses on the core quality of rationalism and rationality. And rationality is the defining feature of human beings. And so she works from there. Whereas Milton Friedman eventually converges on this idea of freedom. So that's one part of it. The other is their intellectual styles are really, really different. Their interpersonal styles are really different. So